excuse me. Okay, let us continue the third part of today's class. Okay, we can see that equation 4.28. Okay, let us see this equation. Okay, equation 4.28. Okay, capital phi c of delta f is equal to the Fourier transform of small c of tau. Okay. So this equation shows that the multipath power delay profile, that is the small phi c of tau, and the spaced frequency correlation function, okay, that is capital phi c of delta f. The two key functions related to tau are a Fourier transform pair as illustrated in figure 4.12. Okay, let us see figure 4.12. So this figure shows the relationship between the power delay profile and the spaced frequency correlation function. Okay, so on the left hand side we can see that it is the delay power spectrum. Okay, the x-axis is tau, okay, is delay, and the y-axis is phi c of tau, which is the delay power spectrum. Okay, and the width of the phi c of tau is Tm, which is the delay spread. And after taking the Fourier transform, we can see that it is the spaced frequency correlation function. The x-axis is delta f, okay, the difference between two frequencies f1 and f2, and the y-axis is capital phi c of delta f, which is the spaced frequency correlation function, and the width of this correlation function is equal to BC, okay, which means the coherence bandwidth. Excuse me. Okay, so BC is typically defined in one of two ways, called the 50th and 90th percentile bandwidth, which we denote by BC50 and BC90 respectively. The nth percentile coherence bandwidth, okay, where 0 is smaller than or equal to n, and n is smaller than or equal to 100, is defined as the bandwidth over which the normalized spaced frequency correlation function is greater than n over 100. Okay, it can be shown that, okay, BC50, okay, please see reference 61. Okay, we see we cite reference 61 again, the book written by Rappaport, Wireless Communications, Principles and Practice, 2nd edition. Okay, excuse me. So BC50 is approximately 1 over 5 times sigma tau. Okay, recall that sigma tau is the RMS delay spread. Okay, so what does this mean? Okay, it means that the bandwidth over which the normalized spaced frequency correlation function is greater than 50 over 100, okay, that is greater than 1 second, is equal to BC50, is approximately 1 over 5 sigma tau, and BC90 is approximately 1 over 50 sigma tau. Okay, so what does this mean? This means that the bandwidth over which the normalized spaced frequency correlation function is greater than 90 over 100. Okay, so in other words, is greater than 0.9. Okay, which is approximately 1 over 50 sigma tau. Okay, and you can see that BC50 is equal to 10 times BC90. Okay, we can use this figure to illustrate it. Okay, for example, I cannot use this, okay, because it is not normalized. Okay, forget it. Okay, let us see example 4.2. Compute the 50th and 90th percentile coherence bandwidths associated with the multi-pass channel shown in figure 4.11. Okay, let us go to figure 4.11. Okay, we can see that figure 4.11 is an example power delay profile. Okay, we have just seen this in today's class. Okay, let us go back to the slide. Okay, 121. Okay, answer example 4.1. Okay, let us go to example 4.1. Okay, in example 4.1, we can see that sigma tau, that is the RMS delay spread, is equal to, I should say, is approximately 82.9 nanosecond. Okay, so example 4.1 showed that sigma tau is equal to 82.9 nanosecond. Okay, it follows that BC50 is equal to 1 over 5 times sigma tau, okay, which is equal to 1 over 5 times 82.9 times 10 to the power of negative 9. Because 1 nanosecond is equal to 10 to the power of negative 9 second. Okay, so we can simply use a calculator to find the value of this equation. Okay, so let us compute 1 over 5 and over 82.9. Okay, is equal to this value, and divided by 10 to the power of negative 9 is equal to times 10 to the power of 9. Okay, so times, okay, 1 and 9 zeros. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so which is equal to this value. Okay, we can see that this value is approximately 2.4 megahertz. Okay, okay, and that BC90 is equal to 1 over 50 times 82.9 times 10 to the power of negative 9. Okay, because we can easily think that BC50 is equal to 10 times BC90. Okay, So we do not need to calculate it again, okay? Or I should say we do not need to use the calculator again. We can just divide BC50 by 10. Okay, then we have BC90, which is equal to 0.24 megahertz and is equal to 240 kilohertz. Okay, before we complete our discussion of coherence bandwidth, it is worthwhile examining the spaced frequency correlation function in a little more detail in order to develop a physical interpretation of capital Phi C delta F. Okay, so when you read the textbook or paper about in the field of communications, okay, please don't just see many equations. You need to know the physical interpretation or the physical meaning of this equation. Okay. To do that, consider equation 4.17. Okay, let us go to equation 4.17. Okay. Okay, R of F is equal to U of F times C of TF. Okay, let me correct the location of this equation number. Okay. Excuse me. Okay, so do you remember what is R of F and U of F? Okay, let us review it. Okay, in figure 4.8, we can see that U of F is the channel input in the frequency domain, and R of F is the channel output of in the frequency domain, and the C of TF is the frequency response of the multipath channel, or you can say transfer function of the multipath channel. Okay, let us go back to page 120. Okay, maybe 1. Oh. Okay, page 123. Okay, which specifies the frequency domain relationships between the LPEs. Okay, this means the low pass equivalents of the transmitted signal U of F, the received signal R of F, and the low pass equivalent of the frequency response of the channel C of TF. Okay, assume that two pure complex sinusoidal signals, that is, signals with the form cosine 2 pi ft plus j sine 2 pi ft at frequencies f1 and f2 are transmitted simultaneously at some time t. Okay, since the Fourier transforms of these signals are equal to delta of f minus f1, okay, because in the time domain the signal is equal to exponential j 2 pi f1 t. Okay, so after taking the Fourier transform in the frequency domain, it is equal to delta of f minus f1. Okay, and the second signal similarly is equal to delta of f minus f2 respectively. Okay, it follows that the received signals associated with these sinusoids are given by excuse me. Okay, sinusoid at f1 RF R of f is equal to C of TF1 times U of f, where U of f is the input signal of the channel in the frequency domain. So it is equal to C of TF times delta of f minus f1. So when f is equal to f1, it is equal to C of TF1. Okay. Otherwise, R of f is equal to 0. Okay, because delta of f minus f1 is equal to 0 when f is not equal to f1. Okay, similarly, the sinusoid at frequency f2 is R of f, it is the received signal, is equal to C of TF2 if f is equal to f2, and R of f is equal to 0 otherwise. Okay, so it follows that it follows from equation 4.26. Okay, let us go to equation 4.26. Excuse me. Okay, in equation 4.26, phi C of delta T F1 F2, okay, it is the autocorrelation under the assumption that the channel is wide sense stationary, is equal to 1 over 2 times the expectation of C complex conjugate TF1 times C of T plus delta TF2. Okay, so back to the slide. Okay, this page. So phi C of delta F is defined as phi C of delta T being equal to 0 delta F. Okay, so it is equal to 1 over 2 times expectation of C complex conjugate of TF1 times C of TF2. Okay, you can see that because delta T is equal to 0, so here is T and here is T, and the delta F is equal to the difference between F1 and F2. So this function is, in fact, the correlation between the channel outputs when the input sinusoids are separated in frequency by delta F, which is equal to F1 minus F2. Okay, so the coherence bandwidth is equal to the frequency separation for which this correlation is large. Okay, so now the correlation, the bandwidth, coherence bandwidth is equal to exactly delta F. Okay, so next let us go to go to section 4.4.2, parameters related to T. Okay, the two intrinsic multipath channel parameters that characterize variations in the T dimension of the channel are the Doppler spread BD and the coherence time TC. Okay, these two parameters are analogous to Tm, the delay spread, and Bc, okay, which is the coherence bandwidth, except that they characterize the frequency dispersion properties of the channel. Okay, what is frequency dispersion? Okay, frequency dispersion refers to the spreading out of signal in the frequency dimension. Okay, next let us see section 4.4.2.1 Doppler spread BD. Okay, the physical cause of Doppler spread. Okay, Doppler spread refers to the broadening of a transmitted signal's bandwidth as it propagates through a multi-path channel due to relative motions between the transmitter, scatterers, and the receiver. Okay, figure 4.13 illustrates the basic principle behind Doppler spread. For a simple case where a transmitter is moving relative to two stationary scattering objects with a stationary receiver. Okay, let us see figure 4.13. Okay, figure 4.13 is a simple illustration showing how Doppler spread occurs. Okay, in this figure we can see that the transmitter is moving to the right hand side at speed v. Okay, and here is a scatterer. Here is a scatterer. Okay, they are both stationary. Okay, in other words, they does not move. Okay. Excuse me. And here is the receiver, which is also fixed. Okay. I believe you that you have learned the Doppler effect when you are a student in a senior high school and in the course physics. Okay, so when the transmitter moves forward to this scatterer, originally the frequency of the transmitter is Fc. However, if the transmitter is moved forward to the scatterer, the received frequency will higher than Fc, and the difference is Fd. Okay, so the frequency transmitted, the frequency of the signal transmitted by this scatterer is equal to Fc plus Fd. Okay, where Fc is the carrier frequency and Fd is the Doppler frequency or Doppler shift. Okay, and because the transmitter is moved away from this scatterer, so the frequency of the signal of this scatterer is Fc minus Fd. Okay, the frequency will be decreased by the amount of Fd. Okay, so the receiver will receive three different frequency components. One is Fc, and one is Fc plus Fd, and one is Fc minus Fd. Okay, so originally, if we do not have these two scatterers, so first the transmitted spectrum, you can see that it is a delta function at f is equal to Fc. Okay, so the bandwidth of the transmitted signal is 0 Hz. Okay, but the received spectrum, we have just said that the receiver will receive three frequency components. Okay, that is three delta function which locate at frequency f minus Fd, Fc, and Fc plus Fd. So this is the BD. Okay, that is the Doppler spread. Okay, it is 25 minutes. See you next time. Goodbye.